If I were to tell you that the cycles of the sun could affect your entire life, you might think that I was suddenly taking a turn away from astronomy and into astrology. While there are many people in the world who believe that you can learn things about your future by studying the position of stars and planets, it's not a position I tend to take on this channel. I'm more interested in the beauty of space and the mechanisms that explain why it is the way it is. But sometimes there is a grain of truth behind even the most surprising of stories. So allow me to put on my prophesying hat. While I'm no writer of horoscopes, I will predict that based on the current state of the sun, over the next few years, you might be more likely to experience bad health, less reliable technology, see warmer weather with fewer clouds, and possibly could be influenced in other surprising ways. How do I know? Because it turns out the sun, that giant ball of fire in our sky, is not just the place we get our energy from. Science is starting to show that its 11-year cycles might just be the metronome measuring out how life on our planet tick, tick, ticks. I'm Alex McColgan, and you're watching Astrum. Today we're going to look at sun cycles. In particular, I intend to show you exactly how the cycles of the sun are already influencing the course of your life. It's no surprise that the sun is influential to life on Earth. After all, in many respects, it is life's origin. Life on Earth needs energy to function, and the sun frequently provides that energy. Light for plants, plants for herbivores, herbivores for carnivores, all the way up the food chain. It's hard to find anything on Earth that could live without our sun. But beyond the gift of that life-sustaining energy, it's easy to think of the sun as fairly static. We see it rise and fall in the sky, but we rarely notice it undergoing any sort of change. This, however, is an illusion. The sun changes all the time. As science has advanced and we've been able to shield out the worst of the sun's glare, it became possible to study the sun's surface. As early as 1610, it became clear that the sun was a boiling, shifting sea of barely restrained plasma, which frequently wasn't restrained. In spite of the intense gravitational force holding it all together, the nuclear reactions taking place in its core are so hot, reaching 15 million degrees Celsius in its center, that plasma bubbles and bursts on its surface, erupting into solar flares that blaze in all directions. Sunspots, dark patches of the sun's surface that are filled with intense magnetic fields and can be between 1,600 and 160,000 kilometers across, form, drift, and vanish. Coronal mass ejections explode out of the sun's corona, the atmospheric zone above the sun that is strangely 200 times hotter than its surface. It's hard to find a place in the solar system that is as active as the sun. What many people do not realize is that that activity waxes and wanes. The sun operates on an 11-year cycle that alternates between a period of low activity, the solar minimum, to a much higher level, the solar maximum, and then back again. Sunspots, solar flares, and CMEs all become more common during the solar maximum. You are 50 times more likely to see a solar flare during solar maximum compared to the sun's minimum, and large CMEs go from happening once every few days to multiple times in a single day. This is known as the Schwabe cycle. Interestingly, this represents one half of a larger cycle known as the Hale cycle, which maps the changes in the sun's magnetic polarity. Once every Schwabe cycle, every 11 years, the sun's magnetic north pole and south poles swap places. When another Schwabe cycle occurs, the poles swap back. Tick, tick, tick. This constant rising and falling of solar energy levels thrums through our planetary system, rising and falling like a heartbeat. And surprisingly, even though we can't see it, we here on Earth move to its rhythm. We don't really understand why the sun goes through this cycle. It's clearly related to the magnetic processes that exist within the Sun itself. Yet, although we have observed these cycles in action for the last 200 years and have seen evidence of their influence on the Earth over the last 10,000, we're still no closer to figuring out why the Sun cycle has a length of that particular time period rather than any other. What force drives it? Lacking any other obvious answer, some scientists have tried to connect the orbital length of Jupiter, also about 11 years, to this cycle length, but this could easily be a coincidence. Although Jupiter represents 2.5 times the combined mass of all the other planets in the solar system, and definitely exerts some gravitational pull on the Sun, its orbit cannot explain the variations, seemingly random, that the Sun's cycle undergoes. Much of what goes on within the Sun is a mystery to us, but its influence on Earth, that is much easier to see. It begins with the space around us. Space is more and more important to modern civilization, so it shouldn't be surprising that CMEs and solar storms streaming out from the Sun more regularly would have an impact on the technology we have up there. Scientists are able to predict the arrival of a solar storm, known as a geomagnetic storm, by the time it arrives at Earth, days or even weeks in advance. This allows astronauts to go into safe shelters to hide themselves from harmful rises in radiation levels, and it also allows the delicate hardware on satellites to be powered down to prevent that hardware from being fried. This is important, as solar radiation can cause unexpected electrical currents to form in wiring, overloading systems that haven't gone into a safe standby mode. But there's another aspect to geomagnetic storms that you might not expect. All of that radiation has an impact on the atmosphere itself. It warms it, albeit just a little. As the atmosphere warms, it expands, and this has an impact on our satellites. In space, there is no drag, so objects can orbit practically forever. Well, this isn't entirely true, and satellites in low Earth orbit do occasionally, about 4 times a year, need to expend fuel to correct their orbits, as there is still a tiny amount of atmosphere up there. But when a geomagnetic storm occurs, the atmosphere blossoms upwards, and low Earth orbit satellites have to maneuver every 2 to 3 weeks to keep from falling from the sudden friction. And this isn't always enough. In 1989, there was a geomagnetic storm that was so powerful it knocked the NASA Solar Maximum mission out of the sky, as an increase in atmosphere suddenly slowed the satellite down. Ironically, the mission had been studying solar flares. This is not an isolated incident. NORAD, the Northern American Aerospace Defense Command, has to relocate hundreds of satellites after each geomagnetic storm, as they have been knocked out of their old orbits. Radiation can also influence our ionosphere, filling it with charged plasma. This can have a slight lensing effect on your GPS systems, reducing their accuracy from within a meter to over 10 meters. The next time you look on Google Maps and it thinks you might be a street across from where you are, a geomagnetic storm might be to blame. Our power grids brace themselves every 11 years for the uptick in these current-inducing events to keep themselves from being overloaded. Amateur radio enthusiasts and airline pilots find their high-frequency radio range dropping significantly as radio waves get deflected or even blocked completely by the more powerfully charged ionosphere. As I predicted in my horoscope, this all adds up to some less reliable technology. The fact that the next solar maximum is expected to arrive soon, in 2025, makes me quite confident in my prophesying. There are some bright sides to this. As space weather becomes more turbulent, parts of the world such as Canada see a rise in the number of auroras dancing hypnotically across the sky. Aurora chasers report rises in sightings from a few times a year to as many as twice a month during the most energetic parts of the Sun's 11-year cycle. So much for the Sun's influence on space and our technology. You might think that that's the end of it. The Sun cycle might influence machinery, but it's not going to make much difference on anything alive, right? If you think that, you'd be wrong. It's not for nothing that the rest of my horoscope mentioned poorer health. There's growing evidence that the sun cycles can even influence ecosystems and species themselves, including humans. Some of this is incidental. When the Schwabe cycle is at the solar minimum, the sun exerts less pressure through its solar winds, which means, ironically, that we get less protection from our heliosphere from cosmic radiation. This form of radiation is highly energetic, but fortunately rarely makes it through our atmosphere for that very reason, as it's likely to be absorbed or deflected by a passing air molecule. But reaching the atmosphere is all that's needed to produce an effect. There is a theory, although still far from certain, that this extra radiation could be creating nucleation sites in the atmosphere that seed extra clouds, influencing our weather. Even if that's not occurring, during solar maximum, the space weather hitting our atmosphere can raise global temperatures slightly. As my horoscope at the beginning predicted, a warming of the weather. Not by much, it should be said, less than half a degree, and the temperature always eventually returns to where it started, but it's enough that it's noticeable to species paying attention to temperature, for instance to decide when to start the mating season. Studies of birds have shown that on warmer years they tend to lay eggs earlier. Curiously, a study published in 2009 by researchers in the Netherlands went as far as to show that the laying times of blue tits were also affected by the number of sunspots occurring, which even the researchers found hard to explain. It's not like birds can look at the sun to see how many sunspots there are. Nevertheless, a link seems to exist, according to the 5 nesting groups that were looked at. This isn't something that affects just blue tits, or even species like homing pigeons that are sensitive to magnetic fluctuations, who fly different routes depending on what time in the 11-year cycle it is. I'm talking about the last unmentioned point in my horoscope, bad health. There are numerous studies on how solar cycles might influence us. In 2011, a study spanning 2 decades of nearly 1/3 of women in Holland discovered a peak in 6 cervical pathologies that took place just after solar maximum, when the sun's radiation was hitting hardest. The study also checked 1 man during the same period, which admittedly is a much smaller number of candidates. Still, it was interesting to note that the man experienced slight elevations in oral temperature, pulse rate, blood pressure, and respiration rate that took place soon after solar maximum too. It's not just physical. There's even an influence on the rate of mental disorders. A study in 2006 looked at 237,000 clients in the main Medicaid database collected between 1995 and 2004. They found that, of all those clients, those born during higher energy chaotic cycles experienced an increased rate in mental disorders. If this is the case, then the cycle of the sun at the moment of your birth might just have influenced the course of your life. It's not quite star signs, but astrology might just be onto something, at least with one specific star. Ultimately, the science on this is still ongoing, and it should be stressed that any health impacts caused by these cycles are extremely minor. As one researcher put it, it took hundreds of thousands of patients to even notice that there was a health impact. The sun cycle should not prevent you from living your life. We're currently heading towards a solar maximum, predicted to arrive in 2025. But for those who are worried, living through or being born in a solar maximum isn't all bad. The same study suggested that this radiation might lead to a rise in creativity and adaptability. Perhaps it was during one such cycle, 80,000 years ago, that a human brain was mutated to give it abstract thought and consciousness. If so, if they gave us the means to perceive the universe, we have much to thank solar maximums for. We wouldn't be us without them. When you think about the North Pole, you don't expect it to go anywhere. And you certainly don't expect it to change places with the South Pole. That would just be wrong. Our magnetic compasses would all point the wrong way. We'd need to update our maps. Birds would probably be horribly confused. And yet, although they sound like something out of science fiction, geomagnetic reversals like this are real. They've happened before. and the process behind it might be a lot more dangerous than you'd think. To be clear, it's not the reversals themselves that are potentially dangerous, it's the buildup. During those times, the Earth's magnetic field, the shield around our planet that keeps us safe from deadly solar radiation, will drop to as low as 10% of its current strength, leading one group of scientists in 2021 to predict climate shifts and mass extinctions, and others to describe satellites being destroyed, electrical grids going offline, and deadly radiation raining down on us for hundreds or even thousands of years. This is troubling when you consider that we are a couple of 100,000 years overdue for our next geomagnetic reversal, and based on fluctuations in the Earth's magnetic field that scientists are detecting right now, the build-up to a geomagnetic reversal may even have begun already. Which begs the question, should we be worried? I'm Alex McColgan, and you're watching Astrum. Join with me today as we explore the science behind geomagnetic reversals and find out whether the next one will be an apocalyptic scenario or whether it'll lead to nothing more than a few lost birds. What truly happens when things go south? Let's start by trying to understand where the Earth's magnetic field comes from in the first place. It's not a given that our planet would have a magnetic field. The two planets flanking us, Mars and Venus, do not have one, and yet the Earth does, which is a good thing, as without one, there is a very real chance life would not have been able to arise here in the first place. Thanks to the protective cocoon of this field, deadly solar radiation is deflected away from the planet's surface, allowing things to flourish without all that radiation breaking down our DNA, causing mutations and cancers. Scientists are still trying to figure out all the particulars of why certain planets have fields and certain others don't, but the current leading theory is that the Earth's core acts as a giant dynamo. It's a principle of physics that you can use electrical fields to create magnetic ones, and vice versa. This is the principle that power plants work under. Moving a magnet through a coil of wires causes electrical current to start to flow, as that changing magnetic field exerts a force on the electrons present there. But similarly, the motion of electrons creates a magnetic field to form in perpendicular circles around the direction of motion, in accordance with Faraday's law of induction. But the way this applies to the Earth's core is a delicate, complicated process. To start with, our core needs to be at least partially liquid, which fortunately is true. Above the solid inner core that lies at the heart of our planet is a liquid outer core, where the pressure isn't quite high enough to keep things in a solid state. It's very hot in the outer core though, 6,000 degrees Celsius at its warmest point, so hot that it rivals the surface temperature of the Sun, which, when combined with the lower pressure compared to the inner core, is more than enough to keep the iron and nickel that makes it up flowing down there. The temperature drops as you move away from the center of the Earth. This gets circulation going. Hot, conductive material from the warmer, deeper regions of the outer core rises, then cools, then falls again, creating loops and currents of flowing material. Our electrical field starts to be generated. But if there are many of these flowing loops, which in theory there would be, why does Earth only have one North Pole and one South Pole? Surely the created magnetic fields would be all over the place. Well, there is thought to be an extra force at play that takes all these fields and unifies them, pointing them in the same direction. This force is thought to be the Coriolis effect. Dynamo theory states that the Coriolis effect causes these flows of iron to not rise and fall as straight lines, but as spirals. The spinning of the Earth causes them to gently be spun in turn, creating giant springs. As each segment of each spring is creating a magnetic field in a circle around it, the net result is that the inside of these springs creates a solid, unified field that all moves in the same direction upwards, while the outside brings that magnetic field looping back down again and back in to the bottom of the coil. In short, it creates the well-known magnetic dipole north and south that we see today. However, if there's anything that you should take away from this, it's that this process is precarious, as it is based on a lot of liquid iron essentially just sloshing around, which is not very consistent. Our magnetic field thus has little fluctuations and wobbles all the time. We see this in different ways, but a big one is that our North Pole is constantly moving. Since scientists began keeping track of it in 1831, the North Pole has gradually shifted about 1,100 kilometers, leaving its original location in Canada and moving up towards Siberia. Its rate of motion is also increasing, going from 16 kilometers a year to roughly 55 kilometers a year, a big jump. This might still be akin to just the momentary wobbles of a spinning top though. Yes, it deviates somewhat, but it always remains roughly upright. That's a far cry from a complete reversal. However, scientists are certain that such reversals have happened before. They even have a specific number, 183 times in the last 83 million years. How do they know? The answer lies locked in our Earth's surface iron. When magma erupts from the Earth's mantle, it can contain small amounts of iron. As these can move freely in the molten magma, they tend to orient themselves in the direction of the Earth's magnetic field. However, scientists noticed that there were layers of geological history where the iron was pointing one way and layers where it was pointing in the reverse direction. Their explanation? The entire pole of the planet had flipped. On average, these flips seem to happen every 450,000 years, although the last few have only got 300,000 year gaps between them. Comparatively, it's been 750,000 years since the last reversal. You might think that we're overdue for one, and some have made that claim. However, scientists have found that there's little rhyme or reason to the timing of these flips. One of the longest gaps between flips took place in the Cretaceous period, and it lasted 40 million years. The record holder, the Kierman reverse superchron, was 312 to 262 million years ago, 50 million years with no reversal. Scientists are still trying to understand what causes these flips. However, the current theory is that something, perhaps some interplay between the mantle and the outer core, causes a fluctuation in the core spinning. This disrupts the spiraling shapes of the core's flow, breaking them down. The magnetic field of the Earth stops being unified and generally becomes a sprawling mess, fighting against itself. Several poles might temporarily arise during this period of shifting magnetic confusion. While in time things settle down and the spirals reassert themselves, it seems random as to which way they will do this, meaning about half the time our magnetic North Pole reappears over the geographical south. This reasserting can take 1,000 to 10,000 years. Alright, but would that really be the end of the world? Why does this matter? Well, during that period before the poles reassert themselves, our Earth's magnetic field drops to as low as 10% of its current strength. In theory, this could leave us much more vulnerable to all the solar radiation space throws at us. We could see auroras reaching much further south during that time. Skin cancer rates would increase. Our satellites would find themselves with not enough shielding. Radiation would fry their circuits, causing them to malfunction, shut down, and potentially even slowly fall from orbit. Our electrical grid would be much more vulnerable to solar storms, which could lead to large segments of the Earth's population without power. With no electricity or satellite communication, it would be a devastating blow to our global civilization. It could be worse than that. A research team from the University of New South Wales in Sydney even linked one of the most recent weakenings of the magnetic field, the Lachamps event, a temporary 800-year wobble rather than a full flip, to megafaunal mass extinctions in Australia, including the deaths of Diprotodon, giant Australian wombats, and Procoptodon goliath, giant kangaroos. Temporary wobbles like this are known as geomagnetic excursions rather than full reversals, and they happen over much shorter time frames. Their transition periods can last as little as 200 years rather than 10,000, which can be much more difficult for species to adapt to. In their 2021 study, they argued that there was a spike in atmospheric radiocarbon levels caused by the collapse of the Earth's magnetic field, indicating climate shifts that could have led to these extinctions. The timing lines up uncomfortably. But how real are these risks? Honestly, it's a mixed bag. A point in our favor is that other than this recent study, there is no indication that magnetic field reversals have ever coincided with mass extinction events. It seems like many reversals have come and gone without affecting animal or plant life at all. And even in this study, such mass extinctions seem to have been limited in scope. There is no claim from the researchers that this was a global phenomenon. Other parts of the world remained unaffected, even during the Lachamps event. It seems that a perfect storm might have been in play, where specific conditions over Australia left it more vulnerable to solar radiation. In terms of our global society, it's worth noting that these magnetic changes would take many lifetimes to complete, even at their fastest. This would be slow enough that we could come to terms with our new reality. If our satellites don't have enough shielding, we would have time to build some that were better protected. If solar radiation becomes a larger risk, we could remain indoors more. Sun cream might become more powerful to mitigate the dangers of cancers, if not remove them entirely. And according to NASA, even if our field were to significantly weaken, it's not like we would be left without protection. Our atmosphere itself can catch radiation, meaning that we would remain safe from solar winds and cosmic radiation, at least to some degree. It would take far longer than 10,000 years for our atmosphere's ozone to be stripped away. But I would be surprised if there wasn't at least some turmoil, at least while we adjusted to living under a reduced magnetic field. Big changes to how a society operates are always painful. And this isn't entirely hypothetical. Did you know the Earth's magnetic field has been steadily weakening for the last 200 years? It would take another 1,300 years for it to vanish completely, so there's plenty of time for it to stop its current downward trend, and there's no reason to think this isn't just a temporary wobble. But on top of that, there is also the South Atlantic anomaly to consider, a section of the Earth's magnetic field that is already showing signs of significant weakening that covers most of the space around South America and the neighboring ocean. This zone might not influence life on the ground, but is dangerous enough that it has fried satellites and threatened astronauts. The Hubble telescope has to turn itself off every time it flies through it. Imagine that, but across the entire globe. That's what we might expect while the poles are reversing. Concerningly, the South Atlantic anomaly has been growing continuously since we started keeping track of it, possibly suggesting the approach of either another geomagnetic wobble like the Lachamps event, or that a full-blown reversal is already upon us. If it happens, it won't likely be something that ends civilization as we know it. But if the study about Australian megafauna is correct, it isn't going to be without impact either. Species could die. Humans will have to accommodate a very different, more hazardous space environment. It's interesting to learn about geomagnetic reversals and their potential impacts on the planet, but while we are not likely to see one happen in our lifetimes, for the generations of humanity after us, this might turn out to be a lot less hypothetical. They might be seeing it firsthand. The Moon. Earth's natural satellite, orbiting approximately 384,000 kilometers away. A celestial object that scientists have studied for thousands of years, using its regular motions to mark the passage of time in calendars. Its dependable rhythms helped ancient civilizations to track when to plant crops, and its waxing and waning phases cemented the moon's place deep in the heart of symbol and tradition. It's a wonder, a necessity, and a curse. While the moon's desolate beauty has captured the vision of poets, it also brings desolation. There is one lunar rhythm that is not helpful to us, a 19-year cycle that brings unexpected floods and ruin. And NASA scientists are worried that in the middle of the 2030s it's about to hit its hardest yet. For ecosystems that are adapted to it in the right way, this won't be a problem. But how adapted are we? I'm Alex McColgan and you're watching Astrum. Join with me today as we learn about the innocently named lunar nodal cycle and why we need to start developing a much better understanding of the fluctuating behavior of our moon if we are to protect ourselves against its dangers. Much like the sun, the moon is an inescapable part of life on Earth. The moon has an immense impact on our planet. You likely have already heard how its cycles influence our wildlife, affect our climate, and create tides. We tend to imagine that the moon and the Earth's gravities cause them to circle each other in a relatively stable, synchronized harmony. But, as is so often the case, nature is not as simple as we imagine it. Instead, every 18.6 years, the moon's orbit undergoes a subtle revolution, a shift in its alignment between us and our sun that causes high tides to grow even higher, tipping us over the edge into dangerous flood territory. But let's delve into what this subtle revolution is. Its name is the lunar nodal cycle, or the precession of lunar nodes. This complex name refers to a specific feature of the moon's orbit of the Earth. You likely know that every 29.5 days, the moon orbits the Earth. However, this orbit is not flat, or, to be more specific, there is a 5-degree difference between the angle of the moon's orbit and the ecliptic plane, the 2D plane on which the Earth orbits around the sun. For half of the month, the moon is slightly higher than the plane of the ecliptic. For the other half, it drops below it. Naturally, this means that there are two crossover points, or two nodes, an ascending node and a descending node, that mark the point where the moon goes from one side over to the other. And it is these nodes that move over the course of the 18.6-year cycle, slowly rotating around the planet in one complete revolution. The nodes themselves are what causes the problem. To understand why, let's recap what we know about tides. You may already be familiar with how the moon's gravity pulls the Earth's water towards it, causing a bulge in sea levels on the side closest to it that we call high tide. You likely also know that this happens on the side of the planet furthest away from the moon. Rather than being caused by gravity, this second bulge is caused by centrifugal forces, as the Earth and the moon's gravitational pull on each other causes them to behave like two dancers holding each other by the arms and spinning across the dance floor. While it's mostly the moon moving, due to the Earth being much more massive, the Earth is also swung around a little. The water behind it is thus trying to fling off into space through its raucous spinning, causing the second high tide. The sun also has a role to play in tide formation, albeit to a lesser degree. It's a bigger mass, which would cause a greater pull if it were closer, but its further distance means that the sun's effect is only 1/3 as big as the moon. When the moon and the sun are aligned, we get extra large tides called spring tides. This happens 6 to 8 times a year. When not aligned, they partially cancel each other out, causing smaller tidal extremes known as neap tides. So now consider the influence of lunar nodes on this tidal tug-of-war. During spring tides, the pull of the sun and the moon working in unison causes the highest tides and the largest risk of floods. However, the sun and the moon are never more aligned than they are at a node. During the rest of each 9.3-year phase, they are not quite tugging in the same direction, so tides are more temperate. At a node, that's where things get more serious and risk of floods become highest. The last time this alignment occurred in September 2015, the UK and the US both issued major flood warnings to its citizens. In September itself, there were floods, albeit minor ones, but it was only when heavy rain combined with the strength of the lunar nodes a couple of months later that the real damage was inflicted. In the US, in October, South Carolina saw flash flooding that caused property damage and people having to be rescued by emergency services. At the end of December 2015, the UK was hit by some of the worst floods it had seen in a century. Combined with the power of Storm Desmond, flooding and storm damage caused an estimated £1.3 billion in damages. These floods can be highly damaging, but that in and of itself doesn't completely explain NASA's worry for the upcoming alignment in mid-2030. There is an extra element at play beyond the regular rhythm of this rising flood risk we have been seeing through the course of human history. Unfortunately, the next node's alignment with the Sun promises to be particularly devastating. The danger is that this phenomenon is combined with an already strained system, even more strained than it was in 2015. Climate change has resulted in steadily rising sea levels. When the next node aligns with the Sun in the mid-2030s, this will likely lead to a dramatic increase of floods on planet Earth. Worryingly, a new study led by NASA's Sea Level Change Science team predicts that almost all US mainland coastlines, Hawaii, and Guam will have a huge leap in flood numbers when this happens. Some predictions claim this node alignment could cause 4 times the amount of flooding from one decade to the next, which will damage infrastructure and change our coastlines around the world. This means human life will inevitably be affected by these floods, impacting shelter, clean water supplies, electricity, as well as the increased risk of waterborne disease outbreaks like hepatitis A and cholera. Plus, the receding floodwater can create stagnant pools of water where mosquitoes gather, which can spread other diseases like malaria. This has a knock-on effect on economic issues, as these natural events can make coastal life unaffordable, with increased cost of insurance on these homes, or an inability to find insurance at all, which could cause a reduction in asset value in the community. Consequently, this lunar nodal cycle will damage the quality of life in coastal communities, where infrastructure may not be rebuilt or adapted to this force of nature. It's not just bad for humans. Ilya Roshlin, a visiting professor at Rutgers University, analyzed that the peak of the lunar wobble, where high tides are higher, can drown salt marshes. Salt marshes are a habitat for a range of species, such as invertebrates, and these floods can cause these creatures to drown, which means that other species like fish, seabirds, and others who rely on invertebrates to survive also suffer. And they aren't the only ones that rely on salt marshes, as salt marshes hold a multitude of marine life, which includes 75% of all fishery species. This means that the lunar wobble impacts the food chains of humans and animals, causing disturbances to their natural habitat and impacting their populations. While this all does seem fairly doom and gloom, it's interesting to note that not all ecosystems on the planet are negatively affected by flooding and high tides. Ecologist Neil Saint-Alain of Macquarie University analysed that the lunar nodal cycle impacts heavily on the expansion and contraction of mangrove canopy cover over most of the Australian continent. The analysis showed that the peaks of the lunar nodal cycle coincided with the cover of the mangrove canopy. It showed that when the lunar wobble is at its minimum phase, it causes the mangrove ecosystems to become very dry, which leads to thinner canopy cover. Yet, when lunar wobble is at its maximum phase, mangrove cover increases. Mangrove canopies are beneficial to Earth's environment as they are complex ecosystems that fight against climate change, protect wildlife, and shield coastlines. They can also absorb 4 times as much carbon dioxide than rainforests of the same size. Their growth is vital to the welfare of our planet, so it's not all downside. Still, it's clear that if we don't plan ahead, coastal cities and environments will face a serious crisis. The all-important question, then, is what can we do about it? One method is better protection. As mentioned previously, the protection and restoration of mangroves can act as a shield against flooding, as they can mitigate the vulnerability of communities on the coastlines. More specifically, mangroves can avert damage by decreasing the height and energy of waves as they pass through mangrove forests. The above-ground roots and branches diminish the height of the waves, and thus the waves lose energy, ultimately stopping the waves emerging onto the seabed and engulfing the sediments. The mangrove's roots and branches also reduce wind energy, which can stop the formation of waves. According to reports, densely packed mangroves can halve the height of a wave through just a 100-meter passage. For comparison, in an open forest where roots and branches are more sparse, it would take 500 meters for a wave to halve its height. So, preservation and reforestation of these mangroves or plants with a similar capability can become a great shield against upcoming floods. Another possible solution is to learn how to live with these flood-heavy conditions, working with nature rather than against it. For example, let's take a look at the flood defenses in the Netherlands, where 1/3 of the country is below sea level, and another third is at risk of flooding. They've built infrastructure that works with water and manages the rising sea levels. They do this by designing facilities like polders. Polders are bits of land below sea level that have been reasserted from a body of water. It's always fully or partially surrounded by an embankment to keep the water out that comes from either the sea or a river. These polders offer a network of drainage canals and pumps to manage water levels by disposing of excess water and running water back to the sea or river to make sure that the water doesn't run over land. Polders can be used to protect houses, farms and factories, and thus are used a lot around the country. The Netherlands also built dams and utilized sand dunes to create ways to stay dry in their swampy land. This shows that there are ways in which we can observe nature and live alongside it. So, the bad news is, behind its ethereal beauty, our moon hides a power that, if just so combined, is set to overwhelm humanity's coastal settlements. However, there's always a bit of good news too, as knowledge is a power of its own. By understanding our plight, we can look for solutions, both among already existing ideas and ways forward that have yet to be discovered. If we are to endure what is coming, it's high time for us to use our innate creativity and drive to adapt and survive, to work with our planet rather than against it. In the middle of the day, the sky starts to darken. It's as if dusk has fallen early. People look and notice something is happening to the sun. A dark shadow moves before it, gradually devouring every last trace of brightness until our familiar lightbringer is only a shimmering, ghostly ring around a pitch-black orb. A total eclipse is occurring. This will soon be a reality. One is coming to the continent of North America in April 2024. But if, like me, you are one of the many billions of people who won't get a chance to see that particular solar eclipse this April, you might be glad to know that America is not the only place they happen. And neither is Earth. Have you ever wondered what a solar eclipse looks like on another planet? Wonder no more. I'm Alex McColgan and you're watching Astrum, and today we're exploring solar eclipses, but not just the ones that happen here on this planet. Allow yourself today to feast your eyes on the actual images and even videos NASA has taken of spectacular eclipses from various places around the solar system. Firstly, I'll quickly explain some of the terminology to do with eclipses. A total solar eclipse is when an object moves in front of the sun, completely obscuring it, also known as an occultation of an object. This is the typical kind of eclipse we see on Earth, when, at certain points in Earth's orbit, the orbit of the moon aligns with the sun. There is something special about an eclipse here on Earth, And I'm not just saying that out of some Earth-focused pride. By a bizarre but highly fortunate cosmic coincidence, the moon is the right size and distance from us that its angular diameter is almost identical in size and shape to the angular diameter of the sun in our sky. This leaves for an impressive spectacle where the corona of the sun, or in other words, the sun's upper atmosphere, creates a ghostly aura around the moon. This corona, normally too dim to see, extends for hundreds of thousands of kilometers into space. Looking closely around the edge of a total solar eclipse, and you will also see the silhouette of the moon's craters along the outside, plus these reddish wisps coming off from the sun. These are prominences, millions of tons of charged particles suspended in the sun's atmosphere by powerful magnetic fields. During an eclipse here on Earth, the moon casts a shadow about 250 kilometers in diameter, which moves across the Earth as the moon orbits. In the case of the eclipse happening this April, this shadow will arrive at the Mexican west coastline, then will make its way up through the United States until it passes into parts of Canada before moving over the ocean once more. You can see on this map the path the shadow will take. If any of you happen to live in its pathway or are close enough to make the drive, you may want to try and see this eclipse for yourself. The sun will only be totally obscured within the diameter of this shadow. Outside of that, the sun is only partially obscured from the viewer's perspective. This viewer is witnessing an annular or partial eclipse, also known as a transit. The shadow moves across the Earth extremely fast, at roughly 1 kilometer a second. Witnessed from a high altitude, it is a majestic sight as the shadow shifts across the landscape. Satellites have also witnessed the movement of this shadow. The shadow isn't as sharp as you might expect, and this is due to the angular diameter of the sun and the moon and their distance apart. The sun itself is huge, a whopping 1.4 million kilometers across. The moon is much smaller, at only 3,400 kilometers across. Now, this image isn't to scale, but it shows visually why the shadow isn't sharp. The umbra is the shadow where the sun is completely obscured, and the penumbra is the shadow where the moon only partially obscures it. This part of the shadow is much wider than the 250 kilometer wide umbra shadow. So why doesn't the moon create eclipses every month when it orbits in front of the sun? Well, this is because the moon's orbit is not in line with the Earth's orbit around the sun. This means there are only a couple of times per year when the alignment is right. This alignment of 3 celestial objects is known as a syzygy. A very cool word, but not something you'll need to remember for this video. I just thought you would find that interesting. If you live in the UK like me, sadly you won't get to see much of the eclipse this April unless you live at the furthest west parts of the country, as the sun will be dipping below the horizon just as it begins. Maybe we will get to see some devil's horns though. Still a spectacular sight indeed. But the Earth is not the only place to experience solar eclipses, and we have the images and videos to prove it. Let's explore eclipses of our closest celestial neighbor, the moon. Because it would make sense that if the moon can occult the Earth, then surely the Earth can occult the moon. And the answer is yes. But it's not the shadow that's the really visually appealing part of this, from the Earth anyway. This is because the Earth is 4 times as big in the moon's sky as the moon is on Earth's. So when the Earth fully obscures the sun, the whole moon is in the umbra. At first, the shadow of the Earth creates a crescent shape. Explain that, flat earthers. But what is different this way around is that, unlike the moon, the Earth has an atmosphere. This means that when the moon is totally eclipsed, the Earth's atmosphere refracts the sun's light around the planet, gently illuminating the moon in a reddish hue. This makes for a beautiful but almost spooky view. The color is caused by Rayleigh scattering, a topic I've discussed in another video. Rayleigh scattering is the same process that makes our sky blue and our sunsets red. This image is beautiful in that you can see the different wavelengths of light being scattered through Earth's atmosphere, from deep red from this side through to blue on this side. From the moon's perspective, none of the sun would be visible during a total eclipse, but the atmosphere on Earth would be illuminated, so you would see a ring around it. This is an actual view of a lunar eclipse on the moon by one of the JAXA probes in 2009. It's quite the awe-inspiring sight. The Earth and Moon aren't just getting in the way of each other either. Here is the Earth eclipsing the Apollo 12 spacecraft in 1969 while it was on its way back home. And here's the Moon getting in the way of the Earth from the perspective of the Discover satellite. Interestingly, this is the side of the Moon you never see, as the Moon is tidally locked to the Earth, which means the same face is always looking towards Earth. From this perspective, the Moon looks very foreign, but it is indeed a real video of our only natural satellite transiting the Earth. From another satellite's perspective, but this time looking at the Sun with the SDO satellite, the Moon often makes an appearance. The position of this satellite as it orbits the Earth means the Moon can block the Sun occasionally. And here's the Moon again, this time from the perspective of one of the stereo satellites. The Moon isn't the only thing that orbits between us and the Sun. Mercury often transits across the Sun, a tiny minnow compared to the solar system's giant. The next time this will happen is on the 13th of November 2032. So a little while away. You might want to put it in your calendars for now. Venus also orbits between us and the Sun, and as it is much closer to us and bigger than Mercury, its silhouette appears much larger. Its last transit was in 2004 and 2012, but sadly if you miss those two, chances are that you will never see it. These transits happen in pairs, and then there is a 100-year gap until the next one. In other words, the next transit will be in 2117. This happens for the same reason the Moon doesn't eclipse us every month. The orbits just don't often align. Still, we have high-definition videos of the last one, and it is quite the sight to behold. Moving to another planet now, we can go to Mars, which has plenty of unmanned robotics either in orbit or on the surface. Mars also has two moons, Phobos and Deimos. They are both pretty small. Phobos is 22 kilometers across and Deimos is only 13 kilometers across. They both orbit very close to the planet though. Phobos is only 9,000 kilometers above the surface and Deimos is 23,000 kilometers, which means although tiny, you can still easily see them from the surface of Mars, especially Phobos. The Curiosity rover was able to capture a moment where, incredibly, Phobos eclipsed Deimos. This video is captured in real time and shows the size differences of the moons in the Martian sky. And this is not all the Curiosity rover captured. It was also able to see a transit of Phobos in front of the Sun. Due to the distance of Phobos to Mars, it moves across the sky fairly quickly, only taking about 7 hours to orbit once. This means that this video you are watching is in real time, and these solar eclipses on Mars don't last for more than about 30 seconds. The surrounding ground does get noticeably darker during an eclipse by Phobos, as can be seen from the rover's perspective, but it can also be seen from space. Phobos' shadow here can be seen by the Viking 1 orbiter, and also here more recently by the Mars Global Surveyor. The Opportunity and Spirit rovers have also seen a transit of Deimos, but it appears much smaller, just a dot passing in front of the Sun. It doesn't cause a noticeable decrease in brightness. Mars is pretty impressive, but that's not all the solar system has to offer. Have a look at this video captured by the Hubble Space Telescope, looking at Jupiter. Jupiter has 4 large moons, 3 of which at certain points can transit the planet at the same time, leaving 3 big shadows. The moons in question in this video are Io, Callisto, and Europa. Interestingly, like we talked about before with the Umbra and Penumbra, you can see that because Io is the closest to the planet, its shadow is the sharpest. Whereas you can see with Callisto, the furthest away of these three moons, the Penumbra is much larger, causing a blurry shadow. And in this video, Hubble spies the occultation of Ganymede, the largest moon of Jupiter. Cassini saw some incredible transits and occultations of Saturn's many moons. Here is one of Epimetheus passing in front of Titan, with Dione coming in from the side. This little white dot coming in from the left just under the ring is in fact a bright background star. And this Hubble view is magnificent. Here are Enceladus, Mimas, Dione, and Tethys orbiting Saturn. Once every 15 years, Saturn's rings and moons are aligned just right so that the moon's shadows stream across the rings as well as on the planet. This video is a time-lapse that lasted 9.5 hours. Amazing. Going a bit further out, we come to Neptune and its biggest moon, Triton. Sadly, we don't have a video, but this image captured by Voyager 2 is gorgeous. 3 days after passing by Neptune, Voyager was able to capture the crescents of Neptune and Triton before Neptune slipped in front of Voyager's view of Triton. Going further out again, we come to the furthest celestial object explored in the solar system, Pluto. As New Horizons whizzed by Pluto in 2015, it turned its camera back towards Pluto to capture the dwarf planet totally eclipsing the sun. What it saw was dazzling. The sunlight streaming through and illuminating the atmosphere and its haze layers, with the ridges and mountains on Pluto's surface highlighted by the stark contrast of Pluto's night side. Occultations and transits may be breathtakingly beautiful, but are they actually useful to us scientifically? Well, did you know that Uranus was discovered to have rings because of an occultation of a background star? As the planet passed in front of the star from our perspective, the star dimmed before and after the planet obscured it. With this information, we are able to count how many rings Uranus has. On top of that, the transits of exoplanets in front of their stars are actually how we can detect exoplanets. Telescopes like Kepler and TESS measure the brightness of stars in the sky. If a star dims, it could be because one of its planets just passed in front of it. If the star continually dims in a pattern, for instance once every 100 days, then we know that a planet orbits that star and takes 100 days to do so. Using this method, space agencies like NASA have discovered over 3,000 exoplanets, more than all other methods of exoplanet detection combined. It can even help scientists calculate the size of the planet by measuring how much the star dimmed, or the composition of that planet's atmosphere by looking at the spectra of the light that passes through from the star to us. It might be some time before we see a solar eclipse again. After the one in April, the next eclipse won't happen in America until 2044. Here in the UK, the next one won't occur until 2090. If I live to see it, I will be a very old man. But I'm amazed as I see all of the images of eclipses that take place throughout the solar system. There's a special beauty to each one of them, a fleeting moment where one celestial body brushes lightly against another, even if it's only through their shadows. Rather than harbingers of doom, these moments fill me with awe and remind me how connected the universe is. Even across thousands, millions, or even billions of kilometers of space, we can notice a planet's passing. And if you're in the right place at the right time, oh, what wonders you can see. Thanks for watching. I was honestly blown away by all the incredibly kind comments and messages you've sent me, and by the numbers of you that signed up to the Patreon. Like I said in the replies to your DMs on Patreon, Everyone here at the Astrum team is so grateful to have such an amazing community. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 patron member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.